Good afternoon, everyone. Glad to be here and glad to see a lot of familiar faces and new faces as well. I learned that my talk yesterday went extremely too long. I promised today to try to compensate for that and be shorter, okay? What we're going to do today, I'm going to finish the last section that was incomplete yesterday. That was kind of, as I mentioned to you, an overview of recent work that my group has been working on. And from that point, I'll start what's supposed to be the second lecture that is more ongoing work. Okay, so let me finish what was incomplete yesterday. You all can hear me well? Okay. So the topics we discussed yesterday was the first one is doing optical spectroscopy using single mode waveguide, and we learned that we've been able to push the technology for spectral ranges, that we can look at several biological materials there, and I showed you some application of that work. And then the second topic I discussed with you yesterday was using that places that you have fluorescence and you want to couple that fluorescence back into an integrated optical waveguide to make devices, and this can be used for several applications, and I mentioned to you a few applications yesterday. What I'm going to do today is actually our last topic is when you don't have any optical transitions available to you. When, for instance, you have this surface that you want to immobilize a biological molecule, and its optical transition is either far from the transmission window that you can collect optical signal. So essentially what you have there is a local refractive index change. So what I'm going to do is, in a way, is tackle the problem of what I discussed with you yesterday, surface plasma resonance, and we'll see how we were able to improve that technology by a few orders of enhancement there. So for those who are not familiar with surface plasma resonance, essentially what you have this gold film there, that's typical thickness there, around 50 nanometers, and you come with light, polarized light. And if you work your classical electrodynamics, when you have a noble metal with a negative dielectric constant and you have a dielectric medium there, you have a surface wave there. It's a plasma wave at p-polarization or transverse magnetic polarization, and that light can propagate at a particular speed. So you just by solving Maxwell's equation on this interface, you find this plasma wave that propagates there with a certain speed. When you come with light and you have that light and you project the k vector of this light beam such that you match the speed that you have that surface wave, the one you got from the plasma wave, you transfer optical waves, traveling waves here to that plasma wave there, and you have an energy transfer there. And if you are measuring reflectance on that configuration, what you see at that particular configuration that you match those speeds, you have a reflection goes all the way very close to zero there. And if you properly design that thickness there, that's when you have very strong resonance there. And this will only happen at particular angles of resonance. Here you want to follow the blue curve there, where you have just water on that interface, and you get this strong resonance of a few degrees there. And this technology, as I mentioned to you yesterday, that's the surface plasma resonance there. So anything that comes to this interface and change the local refractive index there, what you're going to see is a shift of that resonance there. And for instance, in this case, we've modeled a shift on the bulk refractive index of water, and you have this small change on the refractive index, creates a shift, And by detecting that shift, you can retrieve what is that change in refractive index there. So that's the technique of surface plasma. And what we saw that we can do better on top of this is that using the concept I was discussing with you yesterday, we can also, on top, if you design things properly here, you can, instead of using just this noble metal and dielectric constants, if you add a highly transparent material here, an aluminum film there that has, you design this in such a way that this thickness here is just enough to support a waveguide mold. When you have that, you have the formation of a mold that, if you like to simplify things here, in one side you're getting total internal reflection, the other side you're getting high reflection from this metal there. But this is a configuration of a waveguide that you have a coupling procedure from a prism, and this coupling procedure will at the same time transfer energy to your waveguide. As this light propagates, it has a little bit of this mold inside the metal is going to get attenuated. So when it outcouples, as it sees a high refractive index here, that outcoupling process is weak, so the reflection goes down. And this only process, this only will going to happen when I have a small angle. Are we doing the translation, Victor?
Yes, I think so.
Okay.
Хорошо, первый слайд рассказывает нам про поверхностный плазмонный резонанс. Это если мы заводим свет через призму, то при определенном угле ввода наблюдается сильное уменьшение отражательной способности от серебряной пленки. Это и есть тот самый резонанс. Мы видим на графике падение интенсивности, причем очень резкое, практически до нуля. Если по серебряной пленке прогонять воду или воду с чем-то еще, то этот минимум будет сдвигаться, но сдвиг будет очень-очень маленький. Метод поверхностного плазмонного резонанса сейчас является эталонным, он распространен, но его чувствительность чрезвычайно низка. Если мы будем использовать еще и дополнительный волновод, вот из пленочки алюминий-2О3, то сдвиг подобного рода будет гораздо больше, как видно из графика. То есть эффективность этого метода исследования не воды, а чего-то содержащегося в ней, например, биоматериала или химических каких-то растворов, во много раз выше, ну конкретно примерно в 10 тысяч раз по величине сдвига. Спасибо.
А длина волны? Длина волны падающей излучения?
Зависит от того, что мы исследуем. В основном это ультрафиолет, потому что химические, биологические объекты больше взаимодействуют с ним. То есть это не ИК, это как раз ультрафиолет, и это очень неудобно.
Поляризация, я смотрю, там
Поляризация,
одно поляризованное, другое круговая.
поляризация может быть разной. И она тоже является носителем информации. Thank you.
Sorry that I cannot answer the question. Okay. But I trust that you did a good job. So the particular difference here that I want to highlight, both are resonance, both are surface wave. Of course, this one is limited to one particular polarization, that is transverse magnetic. On this configuration here, depends on how you increase the thickness. You first start the initial mode, the fundamental transverse electric mode. As you increase the thickness, you get more and more modes on that structure. And as you're going to see in a moment, we want to keep this structure as thin as possible to support a mold. But if you keep increase the thickness, as I mentioned yesterday, that sensitivity is going to go down. So we want to keep it a single mode. But a key feature here is that you see that the scale on the x-axis here is very different. This one is going from 67 to 83 degrees, and this one is 66.00, and this is 66.40. So this resonance here is way narrow compared to what you have there. And what is the reason for that? The reason for that is very simple. On this truly surface plasma wave here, the propagation loss is very high. So the mode attenuates very fast. When the mode attenuates very fast, by Fourier transform, the angular width is broader. Here, the propagation length is much longer. The attenuation is much weaker, as most of the mode is inside dielectric medium there. Most of the confinement are inside this, the red dielectric medium. So it has a longer propagation length, and a longer propagation length translates in a narrow angular width. So you have a much narrow angular width there. And that will translate on what you see here. The same change that I have in my bulk material there, that I have on the left and on the right, is going to translate into a much larger relative shift here on the right than compared to one on the right. So this means I improve in terms of capability of detecting small changes on that interface. All right, so actually I had this calculation done for quite some time. The big issue here is how to fabricate a high quality dielectric film on top of a noble metal material. We have very few options for the noble metal, either silver or gold, and we did try several technologies along the years, try to get this to work, and all of them failed completely. And we only were able to successfully to really benefit from these calculations that I'm showing you when we start using what I discussed with you yesterday, the atomic layer deposition, that we took this configuration that was done in E-beam evaporation. We have this thin metal film done through E-beam, and then we took that to an atomic layer deposition. We grow layer by layer and making a very smooth interface there to minimize the scattering loss. That was a crucial step. Along the years, we tried sputtering, sol gel, and none of them work. And here is the experimental demonstration that we are able to reach that. On the left is a classical SPR configuration that this is something that is a standard in the industry. You can reach that. And here is our work that we are able to experimentally generate a very narrow angular resonance there using this configuration as we predict experimentally, theoretically. The red curve is the theoretical calculation, and we see the dots there as the experimental work. And with that calculation, I mean, we demonstrate an enhancement of about 20 times over the detection limit that you could get for SPR. Remember that yesterday was mentioned to you, SPR is the current gold standard in the business here in terms of detecting small changes on those interfaces. Here's a configuration that we can do that using very similar, all the technology, all the hardware involved is identical to SPR. Just by adding a dielectric layer there, we can improve the limit of detection. And in this case, you can measure those shifts there even when you don't have any optical transition of the molecules of interest adsorbed to that interface. Essentially, it's going to just change the local refractive index, and you can detect that. Moving forward, what we want to do, what we decide to do beyond that is finding a way that we can detect using that configuration that has a very sharp resonance there, and see if we can do things on a fast time scale. Yesterday was asked, I mean, can we do studies on those interfaces there over the time evolution of that process? Well, we saw here an opportunity that we could just by come with a laser beam, your old simple helium there, and creating a diffraction limited spot here with a decent high numerical aperture there, and from that you have a cone that probe several angles that, and you translate that cone to an ICCD there, where each line of this ICCD corresponds to a particular angle there, where you see that one of those angles corresponds to the resonance of your guiding to your waveguide mode, and you see a dark band. Well, you have those intensified CCDs nowadays that you can get pictures at the nanosecond time scale. So this allows you to do very fast recognition of process that is happening on that interface there. So here is what you see, the black solid line is the one predicted by the theory. The square reds there are the ones that are measured sequentially. Essentially, you're rotating the table angle by angle. That's the previous measurement I showed you yesterday. I showed you on the previous slide. And the one that you see in green, you see on green here, those are measured by just taking a cross-section of this profile there. And you can take pictures there on nanosecond scale, and you can locate what is that angular position there. So this is a case we came in, we absorb a fluorescent molecule on that interface there. Here's the process that we follow, as the dark blue is the one that is the bare, and then we add the monolayer there and let it absorb, and we find the position. There is a shift, and we put a fluorophore there on that interface. And once you have that fluorophore there, we use a nanosecond pulse laser to excite those molecules there, and this light that is emitted by that fluorophore is collected by this ICCD, and we can follow the time evolution of that process. As you see, you have right immediately of this emission process, you get a strong signal. As it evolves, you see this signal goes down. So this facilitates, or this can be applied for, as you use your imagination for any process that you want to study here that has fast dynamics.
Я уверен, что все заметили, что в прошлый комментарий я допустил небольшую неточность. Спешу. Итак, да, чувствительность волноводного метода больше только в 20 раз, хотя это тоже очень-очень много. Но при этом волноводный метод обладает двумя существенными преимуществами. Первое – это то, что потери при распространении излучения гораздо ниже. А второе – это то, что мы, используя CCD-камеру, можем следить за процессом во времени, то есть рассматривать его эволюцию, причем с очень большой точностью, с наноразрешением по времени. Это позволяет работать с быстро протекающими процессами и получать высокую детализацию, то есть получать больше подробностей происходящего. Спасибо.
Professor, one question. Looking to this picture, so we see the minimum its absorption by the water ingredients.
It's not absorption. This is a coupling of a plasma wave. This is, for instance, what you see on this red curve, for instance, or even if you go previously. So there is no material, the only material here that absorbs light is gold. But this is not the optical transition of gold by no means. This is the coupling of, you have either this plasma wave or waveguide waves that you are transferring energy from this light wave to that longitudinal wave there.
And a little maximum near it, it's
this one?
reflection inside the thin aluminum film.
Say again the question.
As I see, the wavelength in the aluminum oxygen 3 is about 1/4 of wavelength. This is why it may be a resonance inside it, and the resonance peak we see in the beginning of your picture. Yes, the first resonance, when it goes up, this one.
Well, this is angle.
Yes, yes.
Okay. So this is the point that you have total internal reflection between your prism and water. So up to this point, you have some leakage of in transmission. When you reach that point, you get total internal reflection. So light, in principle, at this point here, is being totally reflected by that gold that is shiny, and light that doesn't transmit, so you get highly reflection at this point. At this particular region here, that's when you hit that resonance, that you transfer energy to that surface plasma wave, and you have as this couple light into that plasma wave. That plasma wave, in principle, is going to decouple and send light back to this region. But because the metal is lossy, it attenuates the beam, the reflection goes down to zero.
Maybe, but my question was a little bit another. You see, the thin film, and the optical wave is violet zone comes inside it, and you see the multi-reflection between the two surfaces. And when we see the multi-reflection, because it's about 1/4 of the wavelength, as I see, to this picture, it must be multi-reflection inside the film, the thin film. Aluminium or aluminum, yes, it's about 1/4 of the wavelength.
Well,
and it must be maximum, little maximum in this picture as I see. And I ask you, is this maximum which we see belong to the multi-time reflection in the aluminium or 2 oxygen 3 or not?
That's one way to see it. Certainly, you can picture this as a ray tracing that bounces back and forth, and over one round trip, it needs to have a total phase change of 2 pi. So, yes, in this sense, you got to consider not just the thickness, but you have phase shift in particular on this interface, on the top interface. When you add all those phase shift equals to 2 pi, that's the resonance condition. So roughly, that's about, if you ignore the phase shift in reflection, that's about lambda over 2, roughly. So that's a rule of thumb. Yeah, that's how you get this guided mode there. You have this profile there, okay? So what you want to do is excite that mode there. When you excite, this energy starts to propagate. This is a case you have a lossy and leaky waveguide. Well, leaky, if you just had a leaky waveguide, all the energy would come back. But because it's lossy, it attenuates and doesn't come back. Okay? All right, I think that will do for my, okay, so the closing remarks of this lecture was involved that we discussed a lot of the broadband capabilities, and we found that the outstanding limit of detection. We saw the extension to the UV. We saw that we can do molecular orientation, look at order of organic films and on those interfaces. We saw that we can enhance the luminescent process of those interfaces, and we can get sharp resonance that can work even when you don't have transition bands. With this, I think I already mentioned, I have a long list of collaborators that work with me on this. I have a long list of students as well, and I also want to thank the current student that did work here. So with that, I'm going to move to officially the second lecture here, and let me open.
Sergio, can I ask you?
Sure.
What's going to be changed when it's not pure water, when there's some material.
Let me bring.
Before, just some people from biology, from medical department, they are interested if there are impurities of material. Here, just how this curve will change if you put something.
Well, if you put something here, that's what, for instance, here, this something that we model here is a change in the refractive index of your bulk material. So if you just, for instance, if you add some impurities on your water, you put something, disperse something in the water, put a little sugar, disperse or salt, it's going to affect the refractive index, and you're going to detect that. But that's not the big deal here. I mean, that's not the killer application that we are looking for. In particular, we are looking for to detect change here on this interface. And now I'm seeing Boris here. I do remember that he worked on this in my lab, but he worked on a different configuration. So let me tell what the Boris is working on. Did I answer your question?
Yes. Но понятно, что а что если, как это применять этот метод для исследования вещества, которое может положить сверху на вот эту, на серебряную или золотую фольгу, ну, фильм, да, тонкую пленку. И он говорит, ну, ясно, что просто будет достигаться положение вот этого резонансного минимума в отражении. Но и вот Боря может еще пояснить, а для разных целей какая материалов, свойства материалов, понять свойства конкретного белка,
для чего в данном случае более актуально посмотреть абсорбцию данного белка, кинетику абсорбции на вот этой определенной поверхности волновода. И вот именно наносекундный масштаб исследования позволяет это сделать с очень высоким разрешением. Угол резонансный будет смещаться при достижении молекул белка поверхности волновода. Соответственно, поменяется вот этот рефлективный индекс, и мы увидим сдвиг. Вот. В качестве практического применения можно привести ряд биосенсоров, которые сделаны на базе поверхностного плазмонного резонанса, и они уже как бы коммерциализированы во многом. Поверхность функционализируется изначально какими-то сенсорными элементами, ну, биомолекулами, допустим, которым специфично будет связываться исследуемое вещество. И таким образом мы можем, допустим, определить его концентрацию в проби или кинетику его взаимодействия с этой интересующей нас молекулой. Вот это именно наше приложение.
А показатель преломления в воде 1,32?
Ну, 1,33, да.
1,33. И такая добавка и так сильно сдвигает? Да. Это же, смотрите, это же третий знак.
В таком маленьком угле, да? Да. Меняется угле, да, это и борется, что настолько чувствительный метод.
Ну, фантастика, конечно.
Probably I'm the only one that's not following the conversation here, and I may repeat a lot of what you said, but okay. So taking the risk of repeating what we already discussed here, as I mentioned, for instance, this configuration here, this is the major tool for instance, the pharmaceutical industry looking what they do. They mobilize an interface of interest there, and they see the binding of proteins to that interface. So you have, for instance, the bare structure there where you functionalize the surface, and then, for instance, if you want to, when you disperse a protein in solution, when that binds, that's going to shift that peak there. So what we're doing here, we are improving the limit of detection that we can do on this binding process. And for instance, if you want to detect disease, you're going to detect that with 20 times lower concentration, 100 times sooner, for instance. Those are important issues there for many medical and biological applications there. Okay? All right, so let me go back to what I was going to say about the work that Boris did in my lab. So I discussed with you here that in order to do very fast measurement, what we had to do is what we call angle multiplex. We come with a broad range of angles and send that light, and then we collect this sharp transition there. After we finish this work actually was published this month in Analytical Chemistry, so you can find all the details there. You can find that publication in my website there that is illegally posted there. You can download. And, but after we finished this work and we got a new tool that is extremely helpful, what we had is what some people call a white laser, or this is a supercontinuum laser. This is a beam of light that has the quality of a laser beam like this, but instead of being one color, is white. We have all sorts of color. How you do that? You have this, you take a femtosecond laser and you stretch that laser beam over a broad spectral range. Using a photonic crystal fiber. The beam that comes out of that fiber has the collimation of a laser, but it has a broad spectral content. So what Boris was involved in my labs instead replacing this laser beam here with what we call the supercontinuum laser beam. The beam is straight, no lens needed here. The m squared, the divergence of the beam is extremely good. And what we do, we shoot light and we align this to get to the resonance, and we send light this to a spectrometer. And we have spectrometers. Spectrometers are very good to find very small changes in wavelength. So when you come with light with a broad range of colors, just one color is gonna, if you plot not against angle but against wavelength there, you get a reflectance against wavelength, you're gonna see a curve that looks very similar to that. A sharp resonance at one particular color. So then what you do, I mean, you can just keep following how that resonance in color is changing as you are doing your experiment on that interface. So this is very precise. It's way easier to detect very small change in wavelength compared to the one you're trying to do in angle. You want to translate that, or okay. Or Boris should translate that, right?
Просто то, что говорилось сейчас о тех экспериментах, в которые я был вовлечен во время пребывания в университете, это вместо гелий-неонового лазера использовался широкополосный источник света, так называемый белый лазер, supercontinuous. Так и есть, в общем-то. Он обладает практически всеми характеристиками лазера, но может быть разложен на все составляющие белого цвета. И мы наблюдали, как бы отражаемый свет регистрировался спектрометром, и мы наблюдали поглощение в определенной длине волны света. То есть мы наблюдали примерно подобную картину, как и в случае поверхностного плазмонного резонанса. Вот этот угол, это падение интенсивности отражения, просто в характеристиках определенной длины волны света. И также могли зарегистрировать очень незначительное смещение в концентрации монолита. Спасибо.
Did you mention about your acetylcholine experiments?
About my particular experiments?
Yeah.
Well, как в качестве модельных объектов мы использовали несколько белков. В частности, это поначалу был трипсин, это фермент, который расщепляет другие белки, и мы смотрели его взаимодействие с альбумином. Вот эту кинетику, как происходит. Сначала мы помещали на поверхность волноводного устройства альбумин, смотрели, как к нему цепляется трипсин, потом наоборот, ну и исходя из этого делали какие-то предположения. Вот. И второй этап наших экспериментов был, значит, это была попытка формирования некого биосенсора с использованием фермента ацетилхолинэстеразы. Этот биосенсор должен определять ацетилхолин. Это, в общем, тоже физиологически очень активные вещества в нашем организме. Вот. И, в общем, у нас получился довольно неплохой отклик сенсора на базе вот этого фермента ацетилхолинэстеразы на присутствие ацетилхолина. Но это вот пока только инициальные этапы исследования.
А мощность лазера какая была?
Мощность лазера? Что вы имеете в виду?
Ну, оптическая мощность. Сколько милливатт на сантиметр квадратный был поток?
Это я не могу
Порядок.
сказать.
Там не нагревало?
Там мы использовали инфракрасный фильтр. Да, чтобы ничего не нагревалось.
Professor, what about the source power? White laser. Which power do you use?
How much
Milliwatts.
milliwatts it comes? Well, there is a, what you get is about, this is a white light, you get typically around 5 milliwatts per nanometer. So if you consider they have a broad spectral band, the total power if you integrate is around 4 watts across the band. So the technology is based on taking a femtosecond laser at 800 nanometer and you stretch that beam. And you get spectrum that goes from 400 nanometers up to 1.7 micron. Okay.